So in converting these kinds of things to series, one little trick we can use is to recall this identity. So a couple things we need to do. We need to make the numerator 1, and this term in the denominator has to be 1. So we can factor out the 2 easy enough. That's just going to be 2 times 1 over 9 minus x. But then we also got to get rid of the 9. So 2 over 9. If I factor out that 9, that's going to leave behind 1 minus x over 9. And that x over 9 term now becomes your a. So let's play around with that for a second. Let's put it in and come up with our series. So I'll have that's equal to 2 over 9 times the sum from n equals 0 to infinity of x over 9 raised to the nth power. Now a good question would be, well where does that converge? That's going to converge as long as x over 9 is less than 1 in absolute value. So converges when the absolute value of x over 9 is less than 1, which is the absolute value of x is less than 9, just multiplying both sides by 9. And that happens when x is between -9 and 9. That's your interval of convergence. So interval of convergence. Can anyone tell me the radius of convergence? Yeah, it's also 9. So you've got your interval of convergence and radius of convergence. And radius. Nice. Nice. So kind of a nice one to get back into the swing of things here with this one. We are going to move over to our handout next. Are we okay with this one? First one all right? Kind of a nice little warm-up back into this stuff. So let's move over to our handout for example E here. And we're going to start doing other things to try and get our series, including differentiating. So it says, use differentiation to find a power series representation for f of x. Now, all right, we can do that. The nice thing about working with power series is that there's really long polynomials, and differentiating a polynomial is pretty easy. We already know a polynomial for something like this. If we recognize that when we differentiate this, we can get this, then we're in good shape. So let's see what we're going to do here. Right here, this has been written very nicely for you so that its derivative is this function. So let's work on example E here. Example E. F of x is 1 over 7 plus x squared. Now I had to do this work for you ahead of time. That is, integrate this to see what this integrated to, and then I rewrote it in such a fashion that we can plug it in for a series. So that's going to equal the derivative of 1/7 times -1 over 1 plus x over 7. Now that 1/7 can factor out. You can play with this a couple different ways. The excuse me there. The one series that we have right now is when we have a negative in here. If I put this as a positive, then these terms are going to alternate. Let's rewrite this one more time to kind of make it fit our pattern though. 1 over 7, -1 over 1 minus -x over 7, like that. Now we can fit that into our pattern for the series. I'm going to factor out the negative and the 1/7 here all the way out in front. So it's going to be -1 over 7 times the derivative of the series for this term. Now the series for that term, we're going to start out with n equals 0 to infinity, is going to be -x over 7 to the n. Okay, well, let's see about differentiating that thing. Let's see, I'm trying to think if I want to, I'm going to clean this up just a little bit. So that's going to be negative 1/7 d by dx, the sum from n equals 0 to infinity. Now we're differentiating with respect to x. So 7 and the negative 1 here, those are both constants. So I'm going to rewrite this as negative 1 to the nth power, x to the nth power, over 7 to the nth power. So I distribute that power all the way through. But that makes my life a little bit easier. Are we okay with my little change there? I'm going to make another little change. The derivative of the sum is the sum of the derivatives. So I can interchange those two operations. So I'm going to pull that derivative operator inside. Now I'm differentiating with respect to x. So both of these terms, the negative 1 to the n and the 7 to the n, those are both constants as far as the derivative is concerned. I just need the derivative of x to the n. What's that derivative going to be?
nx to the n minus 1?
Yeah, nx to the n minus 1. So I get negative 1 over 7, sum from n equals 0 to infinity, negative 1 to the n, 7 to the n times x to the n minus 1. Okay. Now if I really wanted to, I could factor in that 1/7 in the denominator. That'd be fine. Let's take care of a couple things here so that we can get rid of this out front. Let's do a little mind experiment here. If I multiply that 7 inside here, what's going to happen to this term here? What will I get? Yeah, 7 to the n plus 1. You've got an exponent of 1 out here. So when we multiply that in, you're going to get 7 to the n plus 1. And let's do the same thing with our denominator here, or with our numerator here. If I multiply in by that negative 1, then I'll get negative 1 to the n plus 1. N plus 1. Okay, so looking good on that one. And then finally I've got my nx to the n minus 1. Okay. There is a little bit more trickiness you can play around with, but I think I'm pretty happy leaving it here. You could rearrange things so you get rid of the negative 1 as an exponent here, but I think I'm pretty comfortable here. You can reorder some of these things sometimes. I don't think it's worth the effort for us here. Are we okay with this term here? Let's figure out the radius of convergence then. So to figure out the radius of convergence, we're going to apply the ratio test. So apply the ratio test. So we've got a sub n equals negative 1 to the n plus 1 over 7 to the n plus 1 times n times x to the n minus 1. A sub n plus 1 is going to be negative 1 to the n plus 2 over 7 to the n plus 2, n plus 1 times x to the n. Let's form the ratio of those two things. So it's this one divided by this one. I'm going to do the invert and multiply right away. A sub n plus 1 over a sub n in absolute value. The absolute value is going to get rid of the negatives. So let's see here. let's see, negative 1 to the n plus 2 times n plus 1 times x to the n over 7 to the n plus 2 times 7 to the n plus 1 n x to the n minus 1. Sorry. That part should be in the denominator here, right? Yep. I should have negative 1 to the n plus 2 and this term should be in the denominator. Actually, this term should be in the denominator. N and x to the n minus 1. Let's see what kind of nice cancellation we're going to get out of all this.
Shouldn't the negative 1 on the right side be n plus 1?
Yeah, this should be a plus 1. Thank you. I don't know why I kept on looking at it. This is getting all messed up. My bad. Thanks. All right, let's see. We can get rid of all but one of the 7s. So those all go. Those all go, leaving you with one of them. We can do likewise with the x's. All but one of those go. And then, let's see, what else? You know, the negative 1s, yeah, those cancel. I'm not really worried about those because we're inside the absolute value. So those are really, should probably just ignore them altogether. So you're left with n plus 1 times x over 7 times n equals the absolute value of n plus 1 times x over n times 7. That's how that term simplifies. And I'm ignoring the negative 1 here. There is a negative 1, but that's not going to make a difference in terms of the absolute value. Let's take a look at the limit as n approaches infinity of the absolute value of a sub n plus 1 over a sub n. Now, n is going to infinity, so the x and the 7 are both constants. So I can pull that out in front, x over 7 times the limit as n approaches infinity of the absolute value of n plus 1 over n. What happens with that limit, though? What's that limit going to be? 1. So I really get the absolute value of x over 7 is less than 1. That's going to be true when the absolute value of x is less than 7. For, we've seen this before, negative 7 is less than x, less than positive 7. And that's your interval of convergence. You're not actually going to get convergence at either endpoint, so that's as far as we can go. So that's your interval of convergence. Radius of convergence and interval of convergence. Interval of convergence and radius of convergence. What this means is that we can replace the function 1 over 7 plus x squared by that series as long as our value of x is between these two numbers. If it's between those two numbers, our series and the function 1 over 7 plus x squared are identical. You can use one interchangeably with the other one. That does have nice implications when you're starting to solve equations that require infinite series. And there are some, like the Bessel function. Frederick Bessel. His work predicted the existence of planet Neptune because he saw irregularities in the orbit of Uranus. In any case, Bessel equation is defined in terms of an infinite series. Back to this one, though. We got a couple more parts to do with this one. Are we okay with the first one? Sad? Kind of a grudging nod. It's like, yeah, that felt like a lot of work. All right. But how should I put this? It is a lot of work. Yeah. Now there is a little fact that I'll share with you as we do our next part that's going to help out. So let's look at the next part. It says use part A to find a power series for part B here. So we want a power series for this, and well, we've got a power series for this. How are we going to get a power series for this? Any suggestions? Let me help here. Maybe it would have helped if I called this like a g of x, so that you can look at this and realize that they're different functions. And well, let's see. We've got an x plus, or 7 plus x to the third power. Let me also write that as 7 plus x to the negative third power. And this I could write as 7 plus x to the negative second power. Is that suggesting anything? How might these two be related? Is there a way, is there an operation that we do in a calculus class that can kind of get you close from one to the other?
The exponents are 1 degree apart.
Exponents are 1 degree apart, so
We're doing a use division?
even easier than that. We're decreasing the exponents. It's just the derivative, right? So let's take a look at the derivative of this and see where that gets us. All right, so continuing, this is example E, part B. Example E, part B. Let's see. Let's take the derivative d by dx of f of x and see what we get. So that's going to be d by dx of 7 plus x to the negative second. What's the advantage of writing it as 7 plus x to the negative second as opposed to leaving it as 1 over 7 plus x squared? Why did I take the time to do that?
To avoid the quotient rule.
Yeah, to avoid the quotient rule. Yeah, great minds think alike. Let's let's bypass that. And here, technically we got to use a chain rule. It's the derivative of the outside times the derivative of the inside. Well, what's the derivative of the inside? 1. All right, so let's take a look here. We're going to get negative 2 times 7 plus x to the negative third power, which gives me negative 2 over 7 plus x cubed. Now I've got a series for this. If I take that series, let's see, I want to make that match out right. This is a little bit different than the series that I want to end up with, right? I want to end up with a 1 here. So how can I modify this so that when I differentiate it, I actually get this? What do I have to do? Well, instead of multiplying by a negative 2, I want to divide by a negative 2. So our g of x is going to be negative 1/2 times the derivative of 7 plus x to the negative second. So when we differentiate this, these two terms will cancel out. I'll end up with 1 over 7 plus x cubed. But instead of differentiating this function here, what do you think we're going to do? We're going to differentiate its series. So we're going to use the series that we derived from the last problem. So from part A, so it's going to be the sum from n equals 0 to infinity of negative 1 to the n plus 1 over 7 to the n plus 1 times n times x to the n minus 1. And we're going to have to differentiate that. Now this notation that we're using goes back to Leibniz. And it's very convenient notation. Right now I want us to pay attention to the fact that we're differentiating with respect to n, or excuse me, with respect to x. So the n and the 7 to the n plus 1 all that stuff is kind of like noise. They're constant as far as the derivative is concerned. We're only interested in seeing how things are changing with respect to x. So let's rewrite this as -1/2 times the sum from n equals 0 to infinity. All this stuff that doesn't involve the x is kind of like noise. So it's sum from 0 to infinity, -1 to the n plus 1, 7 to the n plus 1, times n times derivative d by dx, x to the n minus 1. Okay, looking good there. Let's see if we can't clean this up a little bit. What's going to happen when we differentiate this term? Right? What will I get?
N minus 1 x to n minus 2.
Thank you. So n times n minus 1 times x to the n minus 2. So this exponent comes out in front, subtract 1 from the exponent, and we're looking good there. So I'm going to make a little bit of a fix here. Can anyone notice the change that I made? What change did I make here? N equals 2. How come I can do that? How come I can just start it at 2 instead of at 0?
If you cut off any finite amount, the convergence will still be
The convergence is still going to be the same, but these are actually identical in terms of their sum. And what I want you to think about is what happens when you put in n equals 0 here? The whole thing turns to 0, right? What if I put in an n equal 1? Same thing, right? So those first two terms don't contribute anything to the sum because they get wiped out by zeros in this product. Now, sometimes it bothers people to start with 2. It's like, well, I don't really want to start with 2. So maybe we can start with something a little bit different. Let's rewrite this series so that it starts with 0. So my goal is to rewrite this to start at 0. So still, I imagine I'm still going to have that -1/2 out in front. Let's choose a different letter like k. K equals 0. We're going to definitely go to infinity. But now I got to understand the relationship between k and n. How do I get from k to n at the start here? Well, you have to take k and do what? Add 2, right? So k plus 2 equals n. Now if k plus 2 equals n, and I wanted to replace all my n's with k's, let's see if I can't do that. But are you okay with this k plus 2 equals n? I mean, if I'm going to have an equivalent series that starts at 0, then that's going to mean that k plus 2 has to equal n. I can substitute in some things up here. -1 to the k plus 2 plus 1 over 7 to the k plus 2 plus 1. And then instead of n, I'm going to have k plus 2. What's my next term going to be here? If I put in a k plus 2 here, yeah, you're going to have k plus 1. And if I put in a k plus 2 here, I'll have x to the k power. So you're just kind of tweaking this series so that way it starts at 0, which we're more familiar with, and you're not kind of wasting your time here with terms that start out, as 0 as well. Now, do you have to do that to get the problem exactly right? I'm not. if I wanted to do something like this, I might make it as a separate problem, like rewrite the series, because there's just too much work involved here to mess around with trying to figure out all this other stuff on top of this problem. And this problem's long enough as it is. There is one more thing that I could do here, because, you know, -1 to the second power is just 1. I could rewrite this one last time as -1/2 sum from k equals 0 to infinity of -1 to the k plus 1 over 7 to the k plus 3 times k plus 2 times k plus 1.
Shouldn't the negative one be k plus 3 on the top? It's plus 2 plus 1.
Plus 2 plus 1. Well, the thing is, -1 squared is just 1, so I'm kind of factoring that out and throwing it out. So yeah, nice observation. Appreciate you checking me. Whew. A lot going on with that one. Okay. Comments on this one? I guess I could get rid of one more negative. I could factor in that negative, and that would give me -1 to the k plus 2, in which case I could get rid of one more negative, but let's just cut it off here. The little gem that I'll give you, though, is that when you differentiate a series or integrate a series, it has the same radius of convergence. So that's kind of nice. I don't have to look at the radius of convergence. Radius of convergence is still r equals 7. Now, the interval of convergence might change. You might pick up convergence at an endpoint here or there, but I don't think you're going to do that in this case. The interval, the radius of convergence does stay the same, though, so that's a good thing. All right, did a lot on that one. Let me pause for a second, catch your breath, shake out your hand, etc. Are we okay with example B? Is there something that maybe I went over a little too fast? Okay. Let's try. Let's try part C here, the problem that never ends. This time they ask you to find a series for f of x equals x squared over 7 plus x cubed. And you know what? Let me just change something here. Let's make that an h of x, just so that I can distinguish these functions. H of x. If you want a series for this function, do I have to start from scratch? You think I have to start from scratch on this one? Do you feel like starting from scratch? Yeah, I hope that part is clear. Why don't we take note of the fact that this is really 1 over 7 plus x cubed times x squared, or I could write the x squared out in front either way. What's helpful about that observation? Yeah, we've got a series for this, right? We just derived that series. So I'm going to multiply this by the series that we just derived. Let's see, I guess I should, I've got a -1/2 to deal with someplace. Let's just take care of it the right way. -1/2 times the sum from k equals 0 to infinity of -1 to the k plus 1 over 7 to the k plus 3, k plus 2 times k plus 1 times x to the k. Okay, let's do some cleaning up of things. I'm going to finally get rid of that -1 from out in front. So I'm going to multiply that in here. I'm also going to multiply in the x squared. How's the x squared going to change things if I multiply that into my series? Yeah. Thanks, Marlon. So sum from k equals 0 to infinity. And I'll put the 1/2 out front. I've got a -1 here. -1 to the k plus 1, 7 to the k plus 3, k plus 1, k plus 2, and x to the k. Let's just put in that plus 2 there right away. Plus 2. That 2 is coming from there. Now, one last thing here. I'm going to split off one of these k's. And this is kind of what I was doing earlier when Ethan was asking about that missing -1 term. If I take out one of those k's here and put it here, I'll get -1 squared, -1 to the k, over all the rest. The rest is staying unchanged. That's a k plus 1, x to the k plus 2. But what happens to this term here? What's -1 to the second power? 1. So that term can kind of be left off. And you're left with this all together. You can keep the 1/2 out in front. Not a big deal there. Bonus points here. What's the radius of convergence? It's still 7. All right. When you differentiate or integrate, it's not going to change the radius of convergence. The interval of convergence can change. It's just kind of luck of the draw there as to if it changes or not. You have to check those things. Whew. All right. Before your hands cramp up, let's take a look at one last one from this section. And there's good news for you. There's very little writing. I've given you some kind of detailed notes here for you. Before I move on to that, example C, part C, not so bad, maybe. Yeah, not so bad. Okay. This part could be more interactive. So, all the help you give me will actually help the Detroit Lions win on Thanksgiving. So, do your part for the team. You're asked to find a series for f of x as the log of this quotient. And let's see if we can understand what's happening from one step to the next. What's going on from here to here? Yeah, properties of logs, right? So you're just dividing that up. The log of a quotient is the difference of the logs. So your properties of logs. Now what? Now I go from here to here. What's getting me from here to here? Or necessarily here to here? Well, when you integrate these series, you're going to get these logarithmic terms, right? So that much is just integration. And one last little cute thing here. What's going on with the denominator of this first term? How come we rewrote it as 1 minus negative x instead of 1 plus x? Any suggestions?
Fit the series?
Yeah, to fit that into our series pattern. So let me go back to our first page here. We're fitting it into this. So it fits in with a minus x. Now there is one little subtle thing that's going to happen here that's not on this. So let me put it in for you here. I'm going to bring these two terms together. That's going to be 1 over 1 minus negative x plus 1 over 1 minus x, all of that dx. Now the importance of this is that now that we've whipped this into shape, we can replace these things with series. We have a series for each of these. So it looks like this here. Now there's something interesting that happens if you were to expand these series. So if you expand the first one, it's going to look like this. If you expand the second one, it's going to look like this. But something interesting happens along the way. And that is, actually I want to go the other way. Take a look at some of these terms. The 1 and the 1 will add, but the x and the negative x cancel each other out, right? So I get some cancellation here, and here, and then here, and so on. In fact, can you kind of generalize what terms are going to cancel each other out?
Adding an odd power.
Yeah, if it has an odd power. All right, if it has an odd power, it's going to cancel out. If it has an even power, then you're going to get two of them. So that's what this series is here. You've got 2 and then 2x squared and then 2x to the fourth. So you can rewrite this then as a sum of a series with, you know, the 2 there and then an even exponent. Last but not least, when we integrate it, what's this thing here for? We got a C there. Your constant of integration, yeah. We need that constant of integration. Not necessarily in this problem. This problem is going to turn out to be 0, but that is our constant of integration. If you happen to notice that f of 0, if I put in a 0 here, I get the log of 1. What's the log of 1? 0. So plugging that in here, f of 0 equals 0 means that c equals 0. So our function then is really just the sum of this series. You can check that it has a radius of convergence of 1, and it doesn't converge at either of the endpoints. So, whew, nice, nice. Okay, any other thoughts or comments on that one? All right, let's pop this one in for this section.